So let's consider the limit as n goes to infinity of the nth root of n. So we claim that this is actually equal to 1, and we're going to prove this. So here n is supposed to be a positive integer, so n equals 1, 2, 3. And the proof is going to be like this. So first let's consider the case where n equals 1. Then it's quite clear because the nth root of n is just the first root of 1, which is 1 itself. And then if n is bigger than 1, this becomes more difficult. So then the nth root of n is greater than 1. So we're going to let nth root of n be equal to 1 plus something, delta n. And that delta n is going to be a positive number. So now we're going to raise both sides to the power n to get rid of the nth root. So if you raise the left-hand side to the power of n, you get n. The right-hand side becomes 1 plus delta n to the power n. So to do this, we're going to use the binomial theorem, which allows us to compute things like this. So this is equal to 1 to the power of n, which is 1, plus n choose 1 lots of delta n. So n choose 1 is n, plus n choose 2 lots of delta n squared. And so n choose 2, delta n squared, and so on, all the way up to the last term, which is just delta n to the n. So notice that this means that n is equal to 1 plus n delta n plus n choose 2, which is n times n minus 1 on 2, times delta n squared, plus a bunch of other things, which we don't care about because they're all positive. So now in particular, this means that n is greater than this term here. N is greater than n times n minus 1 on 2 times delta n squared. So if we cancel out the n's, we get that delta n squared is less than 2 divided by n minus 1. Therefore, delta n is less than the square root of 2 divided by n minus 1. As n goes to infinity, we know two things about delta. We know that delta n is strictly positive for all n, and it's also less than 2 divided by n minus 1. This term goes to 0, while 0 stays the same. It's a constant sequence. So therefore, by the squeeze law, which says that if a sequence is wedged between two other sequences, and those sequences both have the same limits, then the one in the middle must also have the same limit. So therefore, delta n also goes to 0 as n goes to infinity. So now if we look back, we define delta n to be the difference between the nth root of n and 1. So the fact that delta n goes to 0 means that the difference between the nth root of n and 1 goes to 0. In other words, the nth root of n goes to 1 as n goes to infinity.